Hi everyone, it's Mr. Hamilton here. Welcome to this video on reflection in plane mirrors. This is section 10.2 in the McGraw-Hill-Ryerson Science 10 textbook that we're going to cover. A plane mirror is a flat mirror, just like this body of water is a flat surface. And what happens is light traveling in straight lines will reflect. That means it's going to bounce off of a shiny surface like this water. And so let's look at some examples of reflection. Whenever a ray of light interacts with a surface, it will come in and bounce off at the same angle that it came in at to that surface. And so that what we do is we draw a line that's perpendicular, so this is 90 degrees to the flat mirror, and then whatever the angle that this incident ray came in at, and then notice that angle is measured from the normal, not from the mirror itself, but from the normal. So it's not this angle here, it's this angle up here. That will reflect back at the same angle. So this is a 3D image, so it looks a little weird, but let's assume this was coming in at 30 degrees, then that means this angle here would also be 30 degrees. So the law of reflection says this. Number one, part one of it, is the incident ray, reflected ray, and the normal all lie in the same plane. In other words, if we were to take a flat surface and we were to put it along standing up on end, it would go through this incident ray, this normal, and this reflected ray. The second part of this law says that the angle of incidence is equal to the angle of reflection. And you can see that here again, as we make that angle bigger, there's the angle of incidence, which we label with I, the angle of reflection, which we label with R, and there's an incident ray, reflected ray. Again, those angles are the same, and that we measure the angles from the normal. So what happens when it encounters a very flat, smooth surface like the lake that we just looked at, or like the mirror that we just looked at, the flat mirror, is all the incident rays are going to hit, and the normal is consistently the same all the way along, and so they're going to come off at the same angle. However, if you have a very rough surface rather than a smooth surface, what's going to happen is the normal to this point is going to be a line that may look something like this, right along there. And so the angle of incidence and the angle of reflection is going to be the same, but over here, the normal here might be up like this. And so the angle of incidence and the angle of reflection is going to be very different because that is not a smooth surface. A really cool application of this is the plane that you see in front of you, a stealth jet. And what they're able to do is they design this with the angles so that whatever radar that's trying to pick it up will always be deflected away, so that the angle will never be reflected right back on itself. And so they also have a special paint that they use on it. And what they're able to do with that is actually absorb some of the radar waves. So between those two things, this is a really neat application of this going against the general idea of reflection and being able to use some of the properties to go through top secret without anyone noticing. So with this in mind, we're just going to walk through some of the terms and learn how to draw ray diagrams for plane mirrors. Now we've already gone over this, so this is a bit of review for us, but it's the idea of an incident ray. That is the one that approaches the mirror. And then the reflected ray is the one that reflects off. The normal is the imaginary line that's perpendicular or 90 degrees to the plane mirror at the point where the incident ray hits the mirror. So there you have it right there. There's the normal. It's 90 degrees to that mirror. The angle of incidence is the angle between the incident ray and the normal ray. And the angle of reflection is the angle between the reflected ray and the normal ray. And we already went over the laws of reflection there, that the incident ray, the reflected ray, and the normal all lie in the same plane, and that the angle of incidence is equal to the angle of reflection. So with that in mind, let's look at actually drawing our own diagram and labeling some things on it. Now I know we have the diagram above, but it would be a good time here to just pause it and see if you can label this yourself with all the things given here. We know that this is the angle of incidence, I. This is the angle of reflection, R. Those are equal. We know that this is the incident ray. We know that this is the reflected ray. And we know that the top right here, this line, is the normal. And the angle is always measured from the normal. And so what it says here is draw a ray diagram below in which the angle of incidence is 45 degrees. In order to draw an angle accurately, we need a protractor. So hopefully you have one at home, and if you don't, you should pick one up soon because it is going to be used multiple times in this unit. What we need to do is we need to draw a ray diagram below in which the angle of incidence is 45 degrees. Now you might be thinking, well, I just look here to the 45 degree angle, but if I was asked, let's actually change this to 35 degrees. If I was asked to measure one that's 35 degrees, you might look here and you say, oh, that's 35 degrees. But what would happen if, remember, the angle is always measured from the normal. And so how does 35 degrees compare to the normal? Well, what you have right there is 10, 20, 30, 40, 55 degrees. So you always have to count from the normal. Really important. Always count from the normal. So 10, 20, 35 is actually 65 on the protractor. So that means that the angle of incidence, if we're trying to draw that angle of 35 degrees, is coming along right here. There's my incident ray, angle of incidence. And then my reflected ray is coming off at 35 degrees. 10, 20, 30, and then 35 is right in here. And so using a ruler would be best for this, but you definitely need a protractor as well. And so what we have there is we have the angle of incidence and the angle of reflection, both of 35 degrees, measured from the normal. Now right now we're looking at plane mirrors, which are these flat mirrors, but we're going to look at some other mirrors as well. We're going to look at concave mirrors, and we're going to look at convex mirrors. And you might have seen a concave mirror and a shaving mirror, or might have seen a convex mirror as a store security mirror. Those are to come, but for now we're going to focus on the flat plane mirror. In every single one of these mirrors, we're going to find that we can describe the image that we see in the mirror as its location, orientation, size, and type. When you look at this, L-O-S-T, in other words, lost. That's the acronym we're going to use to remember this. The location can be in front or behind the mirror. And in terms of a quantity, a number, we could say it's X centimeters in front or behind, or some number of centimeters in front or behind the mirror. In terms of the orientation, we would say it's inverted or upright. Inverted is upside down. The size could be bigger, smaller, the same size. And then the quantity, we could say it's a certain number of centimeters tall, or it's a certain number of times magnification or magnified. Now you notice I didn't have any quantitative value for the orientation, because it's either upside down or right way up. There's no number to describe that. And the last thing is type. And we can have a real or virtual type of image. A real image is when the actual light rays come from the object, and a virtual image is when virtual light rays come from the object. The most simple way to describe this is if the light rays form the object on the image on the same side of the mirror as the object, we're going to see that that's a real image. If the image is formed behind the mirror, the opposite side of the mirror than the object, we're going to see that as a virtual image. Again, we can't describe that in terms of a number. We can just describe it as in front or behind the mirror is really what that's saying. So let's go ahead and look at how we draw these in a plane mirror. The first thing we do when we're drawing images in a plane mirror, and that you may notice just from looking in a mirror, is that every time you, like let's say you have a shirt on that has writing on it and you look in the mirror, the words are flipped around. And so what's happened is they've been horizontally flipped. And so you can see that with this letter P. If I have a P that's backwards, what's going to happen is the light rays coming off of the top of the letter P are going to, we have an infinite number of light rays coming off the top. We could have one coming up this way, one coming up this way. We have all these light rays coming off, a whole ton of light rays. We're going to focus in only on two. One that's coming straight out and reflecting back on itself, and another one, again, these are just any two you pick, that's going to come out, and then we're going to make sure that the angle of reflection, angle of incidence and angle of reflection are equal. And so there's the incident ray, there's the reflected ray. And so what you do with these rays, just going to draw these so it's nice and clear for us. There's the incident ray, there's the reflected ray. When we're talking about a plane mirror, we take the reflected ray and we make it a dotted line behind the mirror. And then we take the reflected ray from another ray that I drew from the same point. This one here is coming right along the normal and reflecting back. And we draw that reflected ray as a dotted line behind the mirror as well. And so where those two rays meet is where the P will be, in this case, on the other side of the mirror, where the image will be on the other side of the mirror. And we can do the same thing for another point, just drawing two lines. And this one's convenient because it's 90 degrees, really easy to do. Dotted line behind the mirror. And then the other one, again, we could pick any angle we want, but we need to use our protractor and make sure that the angle of incidence and angle of reflection are the same. And then we take that reflected ray and draw that as a dotted line behind, and where those meet is right there. We do the same thing for this last one right along there. Again, using a protractor to make sure this angle is equal to this one, we draw that reflected ray as a dotted line back behind the mirror, and we find these are the top, middle, and bottom of the P. And then as we know from experience, we can see that that's flipped around in the mirror, and if it's backwards on the one side of the mirror, it's going to be the right way on the in the image of the mirror. Now, this is a perfect example of what we see in everyday life. Maybe you've picked up on this, maybe you haven't. When you see an ambulance driving down the road, have you ever looked at the ambulance and noticed that its lights or its letters are all backwards? What happens is they're expecting you to see that coming back from behind you in your mirror. And what's the mirror going to do? The mirror is going to flip things horizontally. And so what you're going to see is you're actually going to read it in the mirror the right way. So let's go ahead and let's draw this using the following arrow. So I'm going to have my protractor handy. The first thing I'm going to do is draw a line that goes straight from the top of that arrow straight into the mirror. So I have a line that looks something like that. There's my incident ray, and then it's just going to reflect right back on itself. And so if I've drawn that arrow correctly, what I'm going to have is I can continue that as a dotted line behind the mirror. And so I'm just going to, instead of a dotted line, I'm just going to use a different color because it's easier to change the color here than make it a dotted line. So what I'm going to do is I'm just going to take this right here. I'm going to continue this behind the mirror like so. I might have not drawn that exactly perfectly, but it should be pretty close. It's a little tricky here with this. So there's my dotted line behind the mirror. I want to extend it a little bit longer than the other one. And so this is the virtual ray behind the mirror. It's the reflected ray traced back behind the mirror. Now let's go draw another ray here. And I'm going to draw, in this case, a ray that's coming again, but I'm going to make it now at an angle. So it could be any angle. I could put it down here. I could put it up here. But once I draw that first piece, I'm going to make it maybe right there just so I don't have it hitting at the same point I would if I was drawing a straight line on the bottom of the arrow. That is going to reflect off at the same angle at which it comes in at. And so in order for me to do that, I'm going to take my protractor. I'm going to put it right on. It'll be a little tricky to get the protractor to place in the right spot. I'm going to put it right lined up with the edge. If I do this, I should be able to get it to go to the right edge. There we go. I move that down a little bit. There it is right there. So I'm going to line it up exactly lined up at the 90-degree line there on my protractor. So now I'm going to take my reflected ray and I'm going to draw it. You can see there that I'm coming in at an angle of about 15 degrees from the normal. Okay, because the normal is this line here along the 90 degrees. So to be 15 degrees on the other side of the normal means I'm going to start here and I'm going to come out at about 75 degrees according to this protractor. There we go. And now what I want to do is I want to take that and I want to reflect it behind the mirror. I'm going to do that with using a different color. And that reflected ray, I'm going to grab and pull behind the mirror like so. And I want to line it up exactly, and you can use your ruler for this, with the other line. So if I've done that properly, I think that's pretty close for what I have. We should have that. And so what that's going to be is when we draw this new image of the arrow, it's going to be the tip of that. It's going to be the tip like that right there. And so if I do the same thing for the bottom, I'm going to do that with green lines now, and then I'm still going to use red as the reflected lines. Let's see what that looks like. So you can see I've used the green line that comes in and goes off along the normal. That one's pretty easy to reflect behind the mirror. And then I've got another one that's coming in at about an angle, it looks like, of about 109 degrees in the protractor. But remember, that's actually 19 degrees from the normal. 90 degrees is the normal. So I go 19 degrees on the other side of 90, and that's my reflected ray. I trace that behind the mirror, and where that meets the other one, that's the base of the arrow, the black arrow. So this over here is my object, and this over here is my image. So let's describe loss, the location, orientation, size, and type. It is the same distance as in front of the mirror, but behind the mirror. We know the orientation is still upright. It has not been flipped upside down. The size is the same. And the type, because it's behind the mirror, and I've used the reflected rays behind the mirror, that is considered a virtual image. So go ahead and answer the questions below, and then you can check your answers on the sheet that I provide you.